right. Hello, everyone. How are we tonight? Everyone good? Yeah, it's good to be back in Spain. I've been, to Palma. I've been here once before. It's my second time. And it's really good to be back. The weather's really nice. In Melbourne, it's raining. Everyone's complaining it's cold and freezing. So I'm quite lucky to be here. Happy to be here. Thanks for having me. The one problem I have with being in Spain is trying to order coffee. I find it hard. I think it's because the weather is so bad in Melbourne. Everyone drinks a lot of coffee, and coffee has to be really perfect. And I find like the coffee here, it's like there's Americano, but they don't have the same coffee. Right? They put the water first, and then you have to put the espresso, and then you can taste it. You don't mix it, right? So I built a bit of, coming from a DevOps background. So I work for Webjet in Australia. Coming from DevOps background, I wrote a little script, and I didn't use Google Translate anything. I kind of worked it out, and it reads Aqua Primero, Espresso Secundo, Espuma, Ultimo, Gracias, Adios. That's my script. And it's worked really well, actually. I get decent coffee, so that's the only thing I need. And lovely weather. So I'm going to take you guys on a bit of a story. Not too technical, but we'll do talk about technical concepts, but kind of monolithic to microservices. Two massive extremes. On the one side, you've got a really complex system that performs really well because everything is on local host running on the same CPU, but it's really complex, performs well. On the other end of the spectrum, you have microservices, which are really complicated, over-engineered. You got microservices calling each other. TCP becomes a problem. It's really complex. And how did we move from one end of the spectrum to another? And that's kind of the story I'm going to take you guys on tonight. So anyway, my name is Marcel. I'm a solution architect at Webjet. And at Webjet, we're online travel. We sell flights, hotels, cars, and packages. So you can go online and you book a holiday. And I like to work on distributed systems, microservice architectures, and specifically containers, Kubernetes, and Linux. And Linux I find is fascinating. I don't know about you guys, but I think it's absolutely fascinating because all these things about microservice architecture, Docker, Kubernetes, is all built into Linux. Like if it wasn't for Linux, you can't do all this process isolation magic that happens within Docker. So that's why I find Linux extremely fascinating. I also vlog some videos on YouTube. I just started like a few months ago. And that's kind of where I take a lot of these challenges that I learned about, and I condense all the things I find and I make short little stories about it. And I work a lot with a lot of people, different cultures. In Melbourne, we're very multicultural. And coming to Spain, we have different cultures. And I see a lot of the same mistakes happening. So sometimes I like to capture these things, make a 5-minute to 10-minute video about it, how to make a solution on some topic, and I publish it. And that's kind of something that gives me, I like to do that. It's like a passion. And what I also find is my parents and friends, they don't understand. You know, when I do some crazy Linux thing, I can't tell my parents about it. They don't understand what CPU flame graphs are. So it's like YouTube helps. I also do a bit of gym, and I have a website where I put all this stuff on. So anyway, to get to microservices, I'm going to take you guys 5 years back, when I joined Webjet, the Monolith Paradigm. So who here doesn't know what a monolith is? Everyone knows, great. Who here is currently working on a monolith? So day to day, you're working on monolithic systems? Oof. Okay. Yeah, that sucks. Okay. Hopefully you can learn a lot tonight. Because, at Webjet, we still have a monolith, but we also have bleeding edge microservices running on containers and Kubernetes. So how did we get there? Well, for those of you who don't know, you start with a user interface. The company has a website. They put all their investments in there. They build a back-end API, all the business logic goes into that. It becomes really complex, spaghetti code, lots to learn. You get a new developer on board. They have to learn everything. There's just so much tightly coupled code. and you get a large database, and this is kind of the 3-tier architecture that we end up building. And you get some brave people out there that they'll put this all on the same box. So that's some very brave people. But anyway, so Webjet still has a monolith. So I'm going to take you guys on a journey. How did we go from monolith to our first microservice? And the first thing is to identify the pain points. So you have to take acceptance of what you have. You know, if you have like 80% of your team firefighting on the monolith, whether it be deployments, monitoring, errors and things like that, you kind of have to take a stand and say, this is what we have, these are our pain points. And for us, when I joined the company, there were rumors like we took like 5 to 6 months to deploy. So we were deploying really slowly. And a lot of our teams would be involved in deployment. So operations, they would take like a few weeks to prepare for a release. And then when the release happens, they would be on call during the night, releasing. The next day, they would find there's errors. They end up rolling everything back. And it's a vicious cycle. A lot of our teams get bogged down with deployments. And because the monolithic code is complex, so everyone knows this, it's difficult to implement changes. And what ends up happening is the business is pushing more features in than what the delivery teams can actually deploy. And the other thing is there's too many things to test. And when you put features in, you're trying to test, there's so many things to test, you can't test all of it. You end up breaking things. Deployments become really high risk. The problem with this is no one wants to work on these systems. So you have very low morale. No one is excited about deploying tonight. No one is excited to build new features because they don't want to touch that code because they're not responsible for it. And no one wants to work like that. Anyway, so as Webjet, we identified that our problem was deployments, releasing very slowly. We wanted to use some automation around, the key thing is reducing operational overhead. So how do we get all these people that are doing deployments to not have to do deployments so they can focus on better things? And the idea is we target the low-hanging fruit, which was automation around the deployments. So we use technology like PowerShell, Octopus Deploy, very known type of things. And we said we're going to build a button that you can press that will deploy it. So we don't need to involve all the tech leads, the architects, the system admins. We don't have to take them out to do deployments. We can now have a button and press, and we can give it to a BA or a QA or someone who's not really that involved in the code to do the deployments. So we started rotating the roles of deployments through the teams. So our goal was to deploy automatically without downtime. That was the first year I joined at Webjet. We said, we're going to automate this. And the thing about it is when you start automating it, the team actually gets confidence because they know they can just press a button, everything's going to be okay. But the first one is bad. I mean, you press the button and everything catches fire. But the second time it gets better. You iteratively go, regression and make it better as you go along. And the key thing here, when the team gains confidence, the business gains confidence because now they trust what the teams are doing. So it's not now, we give our monolith a name. So it's good to give your monolith a name. That way the business knows Bob is down. They know what Bob is. And from the business point of view, they kind of share the pain. They know the monolith is creating these kind of impacts. So if you can automate, for us, we try to automate this. We make our business more confident because we can release quicker. Some of the business features, we can release it without downtime. So that was the big thing for us. The second thing, and I can't stress this more, is Agile and DevOps. So for those of you who don't know what DevOps is, it's a culture. It's all about trying to merge developer and operations as pretty much bridge the gaps between the two. So sometimes you write some code, you're a developer, you give it to operations, they deploy it, and the two teams fight. There's a lot of clashing. Anyway, so that's DevOps, the culture. We embrace DevOps. I joined Webjet as a DevOps engineer, so my goal was to automate myself out of a job. And to a lot of people, that sounds a bit strange. Like, why would you want to make yourself redundant? But in my mind, if I'm going to go into a team, I can teach the developers how to automate your stuff into production. how to automate testing, how to get better quality code, and show them how to build these tools themselves. That means I can step back and I don't need to be there, and they can increase the quality and velocity at which they deploy. Same thing for BAs and QAs. If QA has a trouble doing some of the quality assurance type of work they do, I can introduce a tool. Whether that tool would be a PowerShell script, or maybe it's a C# or a Python script that I built, doesn't matter. The key is to try and go into the team and automate yourself out of the team. And then you can move to another team that has a need. And eventually, none of the teams will need you. You can start building tools to move all the teams faster and make like group-wide type of decisions. So that's DevOps. In the Agile world, it's a lot about changing the culture of how you work in the teams. It's also about creating work items and deploying them really fast and moving sticky notes on the walls. You got the Scrum, and you can tell I'm a really good Agile coach. I don't know much about the mechanics of it, but it allows the business to really move fast, deploy, get features into production, into customers' hands really quickly without waiting, having high-risk type of deployments. So we form product teams. We started forming teams that says, this team will take care of flights, and this team will take care of hotels, and that team will take care of cars, and we have another team that takes care of payments, and so forth. And that way the team would be responsible for their microservices and their things that they build, and that way, embracing Agile, they can release their features independent of the other teams. Anyway, so to automate yourself out of a job is a key. And really empowering the team to do stuff so they don't depend on you and they don't depend much on each other. They can automate themselves as well. And this enabled us, after a year, we could start deploying weekly. So now we got our monolith to a point where we could have weekly releases instead of 3 months to 6 months, which was a huge thing for us because this allows us now to focus on new things. And at this point, we needed to select our first candidate. We knew microservice was good, but to be honest, Monolith is also good. And Monolith is really good for high volume traffic, doing everything on the same CPU. The code, when you're doing API calls, it doesn't have to jump across many network cards because your database is living in a virtual network right beside it. So there's very little complexities other than developers have to learn a lot of code. With microservices, it's like you have to learn about microservices themselves. They have a lot of things like, where do you store state? Where do you store the data of a microservice? Do the microservices share their data? For example, what happens when one microservice is down? Do you get cascading failure? These kind of things teams had to learn. So for us, we wanted to decouple the monolith, break it down. But this is interesting because when I bring this up, a lot of people think, okay, we have this monolith, we're going to pull out our search, and we're going to put it over here. And then we're going to pull out our booking, and we're going to put it over here. And then we're going to pull out payments, and we're going to move it over here. And the truth is, there's no value in doing that because you end up from something that worked really well, you worked like maybe 10 years on this thing, you're moving it to this other ecosystem, and it creates an over-engineered solution that you end up with problems that you didn't, think about. So don't decouple just for the sake of decoupling. Don't just break it apart because it's microservices. And also, don't over-engineer. So this is something we learned when we decoupled our monolith. And I'll give you an example. The other one is, if it ain't broken, don't fix it. So sometimes it's okay to leave the monolith as is. And you can build microservices around the monolith and start looking at maybe new features you build as microservices. And when you need to, some of the old things you can pull out at some point. But for us, we target, again, the low-hanging fruit. We look at what adds value and MVP, so minimum viable product. And I'll give you guys an example. We had our monolith, and we had a very low critical service with a really high business value. So to give you an example of this, let's say you have a page where you search for shoes. Let's say you sell shoes. And customer searches for a shoe, and they get the results of all the shoe. They pick one they like. It goes to their basket. Now, in many cases, they have to, when they forgot what the shoe they picked, what was the price, they have to go back to the basket. They might lose their search results. So let's say a business feature could be, let me hover over the item and it shows a tooltip with what's in my basket, and that way I can compare what I have. So that's like a basic example of something that could add a lot of business value as a feature, but it's not critical because if that tooltip is gone, let's say that microservice has died, it doesn't really impact the business. The customer can still click on the shoe, go to the basket, do what they need to do, and they can book. So for us, it was picking the features from the backlog that had really high business value but low criticality. So we can say, okay, that's a good example of a microservice. Let's build that. And we would also write it in .NET Core. So we're a Microsoft shop. We quite invested in C#, and we have traditional .NET 4.5 and 4.6. And we said, as this one, we're going to write it in .NET Core because we know there's a value. .NET Core is very portable. It can run in containers. It can run in some serverless architectures and so forth. So how many of you worked on Azure, Microsoft Azure? Okay, it's a cloud provider, and Azure has a concept of IIS as a service. So if you know what an IIS is, it's a component on Microsoft Windows Server where you can host a web application. So for us, we used Azure Web Apps. It's a managed platform, so we don't have to host any infrastructure. It's IIS as a service. So for us, it's like, okay, don't have to manage VMs and infrastructure. So it's a known environment. And we said, okay, there's less operational overhead. We don't have to manage VMs. So this is great. And for us, what we did is we started building automation pipelines to pick this first candidate of a microservice, and we say, we'll deploy it in Azure Web Apps. So this is great because the team don't have to learn too much. It's really easy. You do the same build that you used to do with the Monolith using Microsoft Build. You produce a NuGet package, and you run a PowerShell command to put it in a web app, and you do another PowerShell command to say, make it live. So it was really easy for us to adopt this technology. And we started moving really fast. So we did the first one maybe 3 months, but after that, the next team was already working on the next one, and at some point, we had 60 of these. And this allowed the teams to learn about microservices. They started learning about how should I build a microservice? How much functionality should be in that service? Should it be a nano service where every method is a separate service, or what sort of functionality should we put in there? Also, what data do we store? Do we share data? Does one microservice access another microservice storage, which we probably shouldn't be doing? These kind of things we started learning about, and cascading failures and how to monitor an ecosystem of microservices. And as I said, it's a less unknown environment because it's just managed VMs. And what this allowed us to do is we could start focus on agility. We could look at our DevOps culture. We can look at agile, the way we're working. We can learn about microservices. And it's not too much of a commitment that we picked, it's fairly small scope. And we can start adding value, focus more about the value rather than trying to work with the complexities of the system. So all good things come to an end. I mentioned in the previous slide that we had 60 of these, and this number just kept going up. And with new pain points come new solutions. So we needed more. Azure Web Apps is great. It's good at what it does. It hosts your application with no real issues. But at that point, we just needed more than this. And for us, it became quite expensive to scale. The big problem for us is we have 60 web apps. So normally when you deploy to the cloud, they tell you you're going to have 99.95% uptime. And you think that's amazing. And then you go into Google and you say, what is 99.95%? And it tells you it's few weeks downtime a year. And then you're like, okay, the business is not going to like that. So for us, to get more SLA value out of it, we had to, in more nines, we had to say, okay, to get the SLA, we had to put user availability zones. So that's a common feature in cloud where you say, okay, I want two servers per application. So we end up with 120 servers. Now we've got 99.995%. And I type that into Google, and it's like a few hours a year, and business doesn't like it. It's not good. So we go with, okay, we're going to put this across geo. So we go in 2 data centers, and that's a common thing practice people do. But now we're looking at 240 servers, and that's where cost, we're like, okay, no, we have to put some of them on the same servers. And when we start doing that, you get noisy neighbor. So you start sharing the infrastructure, and it's great because now your cost goes down, but it's only going to go down so much because they keep adding more microservice, and eventually it's just going to tick back upwards. So the other thing is there's a lot more infrastructure than just that, because to do geo load balancing, you need DNS records, you need a DNS load balancer, so you need a little bit more infrastructure, which adds more cost and overhead. And it makes it slower to deploy microservice. We don't want to spend a week to build a new microservice. So release cycles were also not fast enough, because some of these NuGet packages, they get to like 200 MB, 300 MB, sometimes you get 30 GitHub check-ins at a time, and now you've got this times 30. Your deployment pipe gets a bit bottlenecked, and because we got very static web servers for our build infrastructure, running TeamCity or Jenkins, we find that the release cycles were getting a bit bottlenecked. We needed to scale that up. And the other thing with DNS load balancing between microservices, not that efficient. Ideally with microservices, you want it to talk like over subnets, local host. You want it to be really fast because Monolith was fast. You don't want to create 500 milliseconds overhead between microservices. That's not great. So this is where containers come in. And a lot of people ask me, why put a microservice in a container? What's the value of going from a web app, which is IIS, into a Docker container? And the basic answer is you don't get any value because you've moved it from here to here. It's the same thing. It's an endpoint. It's going to give you some response. Not really helpful. So why containers? And the big thing for us is container is an enabler. If you start understanding what is a container, there's a lot of Linux kernel features that allows containers to do really good things. And this is about resource isolation, noisy neighbor, allows us to contain noisy neighbors in terms of memory usage. We can isolate a server, and we can say these containers can only see so much of memory and CPU. That's something we couldn't do on IIS with web apps. The other thing is port mappings. We can tell developers you can use port 80 across all the microservices. And we don't have to maintain an Excel spreadsheet of all the ports and kind of see which one goes to which one. And then you have port conflicts, and it's a nightmare. The other thing is the host machines are immutable. That kind of means that we don't care about the machine the application is running on. We care about the container. So the VM underneath dies, we can replace the VM. And the idea is just give me a kernel. I want a Linux kernel. I don't care if it's Ubuntu, Debian, doesn't matter. Just give me a Linux kernel that's stable and secure, and I want to run my microservice and share the same kernel between all these microservices. And that allows us to reduce cost as well. The other thing is containers kind of promote stateless architecture. So that is about storing data. Microservices shouldn't be keeping a lot of state on disk, because if the container dies, the state is gone, your data is gone. So what we like to do is we try to use cloud to store the data, like an Amazon S3 bucket or an Azure blob storage or some kind of Cosmo DB or something like that. So the microservice stores its data outside of the container. And the other thing is immutable builds. I mentioned earlier we have a TeamCity server that can only handle so many builds. The nice thing with running Jenkins on a containerized environment is, let's say I have 30 Git commits at once, I can spin up 30 containers and do the CI/CD at once, just scale out. The other thing is, we don't have to install anything on Jenkins. This is a huge win. When I was in DevOps, everyone came to me every week. I want Node.js, this version. I want .NET Core, that version. And then I had to maintain a script of what to put on these build servers. And when a build server dies and we need a new one, I could never replicate it. It changed so often. So the nice thing is having only Docker on top of Jenkins the developer can define on their Docker file and say, I need Jenkins, I need Node.js, and I need this version of Golang, and I need this version of .NET Core, and all my NPM packages, NuGet, restore, whatever the dependencies are. It could be some version of Python they need. They add it to Docker file, and Docker files describes everything about the microservice and what it needs. The nice thing about that is if I see a problem with the microservice and the team is having some problem, I can take that Docker file as is and I can do a Docker build on my machine, and I can reproduce the same thing they're seeing. And I don't have to go and find out what they have installed on their machine. And the last one is Jenkins pipelines as code. I don't know if many of you have experienced Jenkins. They have a feature where you can define your whole CI/CD as like a kind of like a JSON YAML type of syntax file. And you can say the first step would be like Docker build. My second step is Docker run. And then you could have like run integration test, unit test. Then you can say deploy, and you can do all your steps as code, which is quite nice. So for us, we said, let's make our microservices very generic. So we create a GitHub repo with some hello world as a source code. We add a Jenkins file to describe the build and deployment. We add a Docker file to describe the microservice and all its dependencies. And then we have an infrastructure file, which is a YAML file which says how to deploy this application. What does the infrastructure look like? And we'll get to that. That's where sort of Kubernetes comes into the picture. So there's only 3 files that a developer needs to know about, and they can reproduce exactly production anywhere. And the other thing I mentioned earlier is describing your whole dependencies in a single Docker file. So there's no other place to go and look if you want to create this microservice. So when we started, this was about, I would think about just over 3 years ago. Kubernetes was very new. Microsoft didn't have an offering for Kubernetes, and because we're quite heavily involved in Azure, Microsoft Cloud, AWS didn't have a Kubernetes offering either. There's generally 3. There's Apache has Mesosphere. They have a container operating system called DCOS, and then there's also Docker Swarm. And at the time, Docker Swarm was available in Microsoft, but it was buggy. So we said, let's try it out. We spin it up. We try run a container. We ran into problems. We then looked at Mesosphere, DCOS, because that seemed to be the most stable one at the time. And that's, for those of you who don't know, I mean, who doesn't know what a container orchestrator is? Everyone. That's great. So just used to schedule containers. A place to deploy your containers, an operating system for containers. It schedules it. It's basically just a scheduler, and it monitors the container health, the probes, and the restarts, and all of that. And it also enforces resource limits. So this was important for us because the web apps we were running on didn't have this feature, and we were running a lot of web apps at this time. So how did we pick which one to use? Because that's quite a question I get a lot. Like, why didn't you pick Docker Swarm? To be honest, like Docker Swarm wasn't, as I said, like it wasn't mature at the time. DCOS was the only one we could choose. Kubernetes wasn't available. So, but the end of the answer is it doesn't matter. It doesn't matter which one. Because we have a Jenkins file, we have a Docker file, we have the source code, and we have some infrastructure file. And we knew that if we go to Docker Swarm, we'll have like a Docker Compose file. If we go to Mesosphere, we'll have a JSON file. And if we go to Kubernetes, we'll have some kind of a YAML file. So it didn't really matter. It's just a matter of changing the file and going. So we said, let's pick this very low critical service, the same methodology we followed for going to web apps. We picked a low critical service, and we said, let's put that onto Mesosphere DCOS at the time. And that's how we kind of picked. So we did not lock ourselves into a platform. We try not to commit to one platform. And what ended up happening was we had some resource limitation on DCOS. And the problem was for us that DCOS, the open source version, did not have secret management. So we couldn't deploy username and passwords in a secret and a reliable manner. And that was an enterprise feature. I don't know if that's changed recently, but at the time, this was an enterprise feature by Mesosphere. And because we're doing this, like we have this one little less critical microservice, we're not going to commit in an enterprise agreement with with Mesosphere for this scenario. So we said, well, let's go without that. Let's deploy the first microservice. And we were live for about 1 week. And then Kubernetes came out. So Microsoft announced Kubernetes, and it's like literally 1 week later, we changed our JSON file to a YAML file, and we created a Kubernetes environment, and we deployed. And we went in blind. We were not experts in Kubernetes at all. We knew how to operate Docker. We understood what Docker run, Docker stop, Docker start, what a Docker file looks like. We understood the basics, but this was all new to us. So we very brave. When I look back at it, it's extremely brave what we did, but it worked. So we deployed Kubernetes, and we went live. So how many of you are using Kubernetes locally in development? Nice. And production? Cool. So Kubernetes is a platform to build platforms. It's one of the biggest things. It's not a place to just deploy microservices. It's designed to schedule containers, and containers can be any type of workload. You could use it for machine learning. You could use it for microservices. A lot of the cloud providers are trying to use Kubernetes to host multi-tenant platforms. And this is what makes Kubernetes really powerful. I'm going to talk about some of the key features that helped Webjet along the journey from microservices to containers, and this is basically it. We could build our own platform from this. We were able to host microservices and have our own API gateway, and I'll kind of show you guys in a little animation that I made how we host our microservices on Kubernetes. And the concept of desired state. So Kubernetes has a lot of services that runs behind the scene that constantly look at the environment. And that's kind of when you look back at traditional monolith, that's stuff you guys were used to do. You used to sit on the phone and you used to look after the environment manually. When the VM dies, you have some alert go off, someone calls you, you have to go in, you have to restart the machine. And this is happening more often, and that the ideology about Kubernetes is let's build desired state configuration so they have all these automation running behind the scene, looking at the environment and saying these things should be running and it will restart it automatically. And the other thing is, what we found with automation in the cloud is you run maybe 2,000 lines of PowerShell or Bash to replicate an environment. And the thing is, those API contracts keep changing. The cloud keeps changing their scripts. So 2-3 months down the line, you've built all this automation. You try and run it again, it doesn't work. And the thing is, the old school scripting mentality, it gives you very imperative functionality, where it means you say, I want this, and then you say, I want that. It's like building a burger, right? You say, I want this bun, and I want that patty, and I want this ingredients, and you're building it step by step. But then when you receive the burger, it doesn't taste like what you ordered. It doesn't taste like what you had in mind. And it's the same thing with scripting in general. You write all this script, and it doesn't give you the exact output. And the idea with Kubernetes is you describe everything up front, what you want, you pass it in, and it creates everything for you. So that's the big difference. Your entire infrastructure described as a YAML file. And this YAML file we give to the developer team, and they describe their microservice. So they say, I want this microservice running that Docker image, and I want 2 copies of it running. And this is my health probe. So Kubernetes can tell whether that container is healthy or not. This is the port I want, and that's the config and the environment variable. So it's very basic. They can add this to their GitHub repo, and they can deploy it on Kubernetes. And Kubernetes runs on Docker for Windows as well, so they can run it locally, which is amazing. So the way to apply it is just say kubectl apply, and you pass it the file. So it's really simple to deploy as well. And it manages ports for the containers. So again, developers can just run across a standard port. They don't have to worry about how the network hops is happening in terms of getting the request from the browser into the microservice, just standard ports across the board. The other thing is Kubernetes has an internal DNS. So every microservice we used to build on web apps, we had to ask our operations team to get a DNS created for that service. The nice thing with Kubernetes is it has an internal DNS. So if you name your microservice Bob, you'll get a DNS entry called Bob, and you can start calling that DNS internally. And for the external traffic, it has a concept called ingress. So a developer can, again, use this YAML file, and they can say, I'm expecting traffic on bookingapi.webbeds.com, and I'm expecting to use the path/book, and they can submit that as their YAML file, and Kubernetes will handle the ingress of that microservice. The other thing is Kubernetes uses a concept of deployment and pods. So a deployment object is kind of like, how do you want to deploy? Do you have a web server? So web server generally, if you have 2 replicas, Kubernetes will roll out an extra replica when you do updates, cancel one of the old ones, create another one, cancel one of the old ones. So it uses a graceful type of deployment. And you can describe this in the deployment object. If it's a cron job you're running, you could just do an emerge, like a kill of the current one and just recreate. So deployments describe how you want to deploy. The pod describes what is the microservice, what port does it use, what config environment variable it needs, what Docker image it needs to run, what version. So with that, I created this little animation just to show you guys how we use Kubernetes at Webjet. And basically, from a very high-level point of view, we have all this infrastructure that gets created. And we use Kubernetes AKS, which is a managed version of it. So we don't have to manage the master nodes. So we have, like, let's say 5 VMs. And what Kubernetes does is it creates an API server on top of it when you deploy it. And Kubernetes has its own database. And what Kubernetes does is it also it calls the VMs actually called nodes in the Kubernetes world. And the API server, or the developer, has a YAML file that they pass to the Kubernetes API to say, this is what I want, you can go create it for me. And so this is the nice thing, because in our microservice, we can have this YAML file in Git that I described earlier. The developer says, I want a deployment, I want 3 replicas, and I want a graceful style of deployment. They also describe their pod. They give it a name, they give it a port, an image, and environment variables. And when they submit that to the Kubernetes API, and we use Jenkins to do this, so Jenkins would submit the YAML file to the Kubernetes API, we'll get 3 containers running on these on these nodes. So we don't have to really look after the machines themselves. The machines are basically one unified pool of compute. And that's nice because we use open source monitoring, Prometheus, Grafana, and we run Prometheus on these machines. And what Prometheus does is it aggregates all of the capacity together, and we can see what percentage of memory we're using on the entire environment. We can also drill down to each machine and see we're using X amount of memory or CPU on that environment and disk. And we can look at capacity planning, and we can scale out the nodes without worrying about the containers running on top of them. So when we apply this YAML file, we get now 3 containers running on these VMs. And what happens is, in the night when we're sleeping, one of the VM dies. And this happens in the cloud. A VM disappears. What Kubernetes does is it constantly tracks the database records. This is a desired state. So it says, it looks at this contract that the developer has submitted and says, I need 3 replicas always. And now there's only 2 replicas running. So it looks at the desired state and automatically creates a 3rd one back on one of the nodes that's running. And this is the power of Kubernetes, because VMs in the cloud can come and go. And we don't want to have to wake up at night and reboot machines. And this is why health probes are important. So when you build a microservice has a health probe entry. It's just an endpoint on the microservice. And if that endpoint becomes unstable, Kubernetes will do the same thing. It will actually move it to another machine. And this happens often with processes that just hang, if they hang for some reason. Or it could be processes using too much memory. So we refine a memory limit for what the process can use, and they have a memory leak. And what will happen is Kubernetes will detect this and automatically kill that container gracefully and start it somewhere else. So this takes a lot of overhead away from operations. They can kind of go to sleep at night. And we also run an application called Fluentd. I don't know how many of you know about Fluentd. It's an application that we run on every node. So Kubernetes has a concept, they call it daemon set. So it's another YAML file exactly like that. And you say, I want to run this Docker image, and Kubernetes will distribute it on all the nodes. And what Fluentd does is it looks at the Docker logs on every node, and we push it to our logging provider. So you could use Kibana with Logstash and Elasticsearch, or you could use a hosting provider like Sumo Logic, and we pump out all our logs. So a developer doesn't have to write commands or write programming language to say, I'm going to push this log out. They don't have to know about where the logs go. We automatically pick the logs out, and that allows us to create alerts. When containers restart or when there's crash logs, we can immediately be alerted. The other thing is, when that node comes back, we can see it came back. This happens in the cloud. A VM dies, and then it comes back magically. And what happens is it just joins the pool of compute again. So another container can then schedule on that node. Now, Kubernetes has another thing, because at this stage, our microservice is not publicly accessible. It's just 3 containers running. Kubernetes has a concept of service. So it's got another object. So we talk about deployment object. We talk about pod object. This one is called service. And it basically describes how does Kubernetes handle traffic for that microservice. When we apply that YAML file to the Kubernetes API, again, through Jenkins and our CI/CD, Kubernetes will create this service object, and it uses technology under the hood like IP tables and IPVS, which are Linux concepts, to create an internal routing for that microservice, and it has internal DNS. So at this point, if we call our application Bob, we'll have a DNS entry called Bob, and any other microservice in the cluster can access that microservice just with http:/Bob, and it will work. The other thing that Kubernetes does, it's possible to do, is if you change the type of that service to load balancer, Kubernetes will figure out that it's running in Azure or AWS or Google Cloud. Doesn't matter where, it will figure it out, and it will go to that cloud provider API, and it will go and create a load balancer with a public IP. So this is something we do, but we don't do it for every microservice, because we want the microservices to talk over internal DNS. So what we do is we use the concept of ingress. So Kubernetes has an ingress controller, which is another microservice. Just like every other microservice, it also has a pod deployment spec and a service, and it is of type load balancer. So it gives you a public IP. And ingress is almost like an API gateway. You can kind of picture it as a public endpoint where all your requests come in, and that API gateway decides where it's going to go inside of the cluster, to which microservice. And then you can decide based on your architecture, I want this API to be public, but these APIs I might want to be private. So they can use the internal service or they can use an external service. The other thing Kubernetes has is the concept of config map and secrets. So it's another object where you can just say, I have this JSON file, and that could be like an app settings config file. It could be your config file with all your external provider entries, or your database connection string. Connection string you would put into secrets. And the cool thing with secrets is that your operation team can apply the secret. So maybe operations has, or your SecOps team, security team has the connection string, and they can go to the API server with a YAML file. They can apply it and give it a name. So they can call the secret Bob. So the secret's name is called Bob. And then the team who is responsible for that service, Bob, can just in their YAML file make a reference to say, I want to use that secret. And Kubernetes will go grab the password and mount it into the container. So it allows that kind of separation where we don't have to share much secrets across a team, but it gives the team flexibility to deploy without having to leak passwords all over the place. So this is kind of the basic setup of how we use Kubernetes at a very high level for folks who are new to it. I didn't want to go into too technical for folks who are very new. So the basic things you need to understand is deployment, pods, services, secrets, and config maps. And then the next slide, I'll show you guys how we manage the ingress traffic. So this is something that was quite a big win for us when we moved from web apps into Kubernetes, is we can have one public endpoint. So the cool thing is operations can add the SSL cert for us as a secret, and they can add a DNS, and they can bind it to that public IP. So what ends up happening, so what we do is we have the Kubernetes API as before. we have a YAML file, let's say operations or your DevOps engineers, they have this YAML file, they create a namespace. And a namespace is like an area where microservices can be deployed or any resource. It's like a logical grouping of resources. So we created a namespace and we call it ingress. And then what we do is we create a deployment. And in the deployment, we might say replicas, we want 3 of them minimum to run. And you can scale this up based on your demand. So if the edge of your cluster requires to handle more traffic, you can scale it up. And we use the Nginx version of a deployment. So this thing can handle quite a lot of requests. And its logic is just to pass the traffic through to microservices. So very low overhead. Doesn't use much CPU, doesn't use much memory. It just passes the traffic through. So in the pod spec, we run the Nginx ingress controller. And then we have a service of type load balancer. So just like I had before, I have this YAML file, and then when we apply it, we get a load balancer with a public IP. And we have this ingress controller, and the cool thing about an ingress controller, you have multiple different types of proxies. You have Nginx, you have traffic, you have Envoy proxy, you have HA proxy. There's a bunch of different technologies you can use. But the cool thing about ingress is the developer and the operations team doesn't have to learn about Nginx. They don't have to know about whether it's HA proxy doing all the work because it's a simple YAML file. So I'll show you guys now the YAML file that the developers have in their GitHub repo for the microservice. They can control how the traffic comes into the environment. So they create a namespace. So we have a team at Webjet. As an example, we have the flights team. And they have a namespace called flights. And then what they do is they have a deployment. This is an example of a deployment they might have is the flight search service. It's a microservice that's responsible for taking all flight searches that come through the website. And what they do is they have a service, just like the YAML I showed you guys earlier, but they have a type cluster IP. So that means this is a private service. Cannot be accessed from outside. It's running inside a VNet, and it has a private IP. So how does this now take public traffic? And that's what they have in the YAML file is they have an ingress endpoint. And in the ingress declaration, they say, what host am I expecting the traffic from? And there you could say flights.webjet.com.au or api.flights. Whatever host name you want to define. And because we have one entry point, we may have like a api.webjet.com.au type of host name as a DNS. And that's the one operations would bind for us in the beginning, pointing it to the ingress controller. Developers can just say, okay, I'm expecting traffic on that host. And more importantly, I'm expecting it to go on that path, so /API/flight search. So that's kind of what the request would look like when it comes to the environment. And the magic that'll happen is Kubernetes is watching for these ingress resources that comes into the API server automatically. And when they come in, Kubernetes or the ingress controller will take that YAML and it will create a rule inside of Nginx. So it generates an nginx.config on the fly automatically and hot reloads that into the proxy. So the same thing would happen in an HA proxy or any other kind of ingress controller that you might use. And that means the developer doesn't have to know about an Nginx config. They don't have to understand how to write it, the syntax and all the things that Nginx comes with. They don't have to care about it. And when they supply this to the Kubernetes API in Jenkins, Kubernetes goes to that ingress controller, which happens to be Nginx, and it creates a config entry in there, and it reloads it. And this happens in like milliseconds. It's really fast. So then what will happen is the ingress will then route that traffic into the service. And when that service gets the traffic, just like the previous slide I showed you, it'll go to the microservice. So in this case, the developer said, I want 2 microservices, and I want to use a cluster IP service. So technically, this is all private, but it's accessible via the ingress. So the benefits of that is when you run things like .NET Core, you run maybe a Golang microservice, you may be running a Java, Python, using Flask. These services are not always meant to be directly accessible by the public because their attack surface can be quite large. They can have vulnerabilities as well. So it's good to access them through a proxy. So Nginx mitigates a lot of this risk because now the public hits the Nginx endpoint and Nginx then routes internally. So it helps us mitigate that risk for HTTP attacks. Similarly, if another team comes across, they have a bookings API microservice, they'll have the same type of YAML. They'll have a namespace with maybe their team name, they have their microservice and their ingress, and when they apply that, that config gets hot reloaded automatically as well. So now they can accept traffic on the same domain with maybe a different path, and that'll hit their microservice. And the nice thing with this is because we have Fluentd ingesting all these Docker logs, we can turn Nginx logging on to say, give me all the requests coming in. And this helps us to track all the requests coming into the cluster, and developer doesn't have to really log the incoming requests. So we can see web requests coming in, and developers can log errors in their services. And this kind of helps us to, as DevOps, automate the whole thing from logging to monitoring. We use Prometheus heavily at Webjet and WebBeds, where we actually try to use decentralized monitoring. So every microservice would have like a metrics endpoint, and Prometheus would go and scrape that service. And that's something that really helped us to build monitoring around the microservice ecosystem. So given we're at this point in the journey, we start building a lot of microservices. I think Webjet, when I last looked, we had about just over 300 containers per environment running. And here at WebBeds, we're going on the same journey, and we're going very fast. So we've already got a couple microservices. We're going to be approaching 100 soon, I can imagine, with the velocity I'm seeing in the teams here. But what is next? I mean, we've got the build figured out. We've got the testing figured out. We have the CI/CD. We've got the monitoring in place. But for us, this is the next bit, is the exciting part, because now at WebBeds, we have a very high volume traffic demand. So the noisy neighbor concerns we had with web apps is going to be times 100 when we work in the WebBeds world. So for us, it was about scaling for performance. So now we can say, how do we have, like, used to have 60 web apps, now we have 300 containers. How do we make this number higher without increasing our cost too much? Because we don't want to keep adding machines. We want to start looking at like 100,000 requests per second type of volume. How do we scale linearly? So when we add a new microservice or we scale up, we see the number of requests per second going linearly. We don't want it to flatten out. So that's a big challenge for us. How do we scale the environment? And how do we scale Kubernetes? And how do we scale the cloud? So it's a lot of, sometimes you might find your monitoring becomes the bottleneck because the microservices are flooding the monitoring system. That's why we use Prometheus, because it uses a pull approach, so we don't have that problem. But similarly, when you scale to this type of volume, you don't know what's going to happen. So this is kind of the exciting part for us, is how do we scale? And how do we schedule for scale? So we talk about Kubernetes automatically moving microservices across VMs. How do we make sure that when it's moving this microservice, that's not an important database? That could be your payments database, and now Kubernetes is moving it because it thinks, you have to understand quality of service. So there's like all these things. We have to understand what impact does CPU and memory allocation have. When we tell a container that you can only use one core of CPU, what is the impact of that? What does Linux do under the hood? Does it throttle? What does that throttle result in? Could be now all of a sudden your scaling goes down because it's throttling. So these are things we're quite excited to be working in, and capacity planning. How do we scale, again, infrastructure and the containers? Quality of service. How do we run really important workloads that can't be interrupted? And then some of them might be less important that we can move around. And multi-tenancy. So that's quite a big one. We're finding, like, how do we have a team with their microservice live in harmony with another team on the same cluster, without teams blaming each other? No, yours is eating all the CPU or memory. And the other one is just performance engineering. We've been looking a lot at the community about, the cool stuff they're doing with Linux. And one of them is like flame graph analysis, where you can take all the call stacks out of the Linux kernel and .NET Core. Like every process basically does a lot of call stacks. So if you know what a stack trace is in the errors, when you get a stack trace, that's a call stack And the operating system has call stacks that are below your call stacks. So there's a lot of concepts, and one of them is called flame graph analysis, where you can see where the CPU becomes busy. So we start looking at some of these things. How can we get this metrics out without profiling the system and making it slow? And the other thing is the development experience. And this is a very important part. When you're onboarding new teams, you don't want to have to give them a 2-3 year degree on how to write YAML in Kubernetes. It doesn't add business value. You want them to be able to build locally and confidently be able to deploy the same thing to production and understand and share that knowledge end to end. So this is the exciting part for where we're at in the journey. And I think there's a lot of cool stuff happening here. I'm super excited to be here because I feel like WebBeds is doing so much in this space and moving really fast. And yeah, so we are hiring. I know WebBeds is hiring. They have the email there. Is Marcos is somewhere in the crowd. If you want to speak to Marcos, if you're interested. Yes, I feel like it's a really exciting point we are in the journey where we are with microservices, and we're moving extremely fast. And it's like I've got to try and keep up with the technology, and it's just it's quite exciting. But that's everything that I had to share. Probably got some time for questions.